Okay, the exam score is already available on LEB2, right? Yes, so that you can see your score, max, min, average, and then solution of the exam will be available after class today. So just to make sure that we focus on the class material first. Code. Okay, so that today we move on to a new topic, which is about algorithms and their complexity. Okay, because last time we talked a little bit about this as well, right? That basically, okay, we're gonna see like the description of the algorithms, okay, what they are, and then like, so this is very related to other courses that you have now, right? So programming language and what else? Do you take data structure now or soon? Okay. So that the outline of today's lecture is here. That first we're gonna go to through definition of algorithms, some example of them, and then see how we analyze for the complexity of the algorithms and functions. Okay, and you see like how important they are. Okay, so basically, okay, as a like engineering student, okay, we have to work on like problem solving, right? Like technical problems where algorithms or techniques are used, okay, to solve the problem. But before that, right, the problem has to be well defined first, right? We know exactly what is included or excluded in the problem. We know about the input and expected output as well. So basically, the algorithms or techniques contain steps, okay, steps to solve the problem. Let's see the definition here. That algorithm consists of just a number of instructions, right? Finite number of instructions to solve the problem or perform the computation, right? There are many algorithms out there, okay, because we have many different problems, right, that need to be solved. So that, let's see, okay, in order to specify or present an algorithm, normally we would use a pseudocode, okay, pseudocode. So that means it's not a real code, right? Not exactly in Python or Java or C, but like a more like generic code, right? That everyone can understand, mostly like we, right? No matter what programming language that we are familiar with. So that the pseudocode can be used, okay, for like analysis to find out like if the algorithm is complex, okay, how complex it is. This is independent of specific programming language. Let's see about the properties of algorithms. Okay, these are required. That is, okay, that it receives input, okay, input data. It gives output. Okay, so output is the solution, right, of the problem that it's solved. The algorithm must to be a valid algorithm. It must give correct result. Okay, correctness here, correct output by performing a number of steps to solve like right, a fixed, okay, a finite number of steps to solve the problem, right? After taking the input, the algorithm must be effective. So that means not only giving correct output, but also like just within a certain time, right? It cannot just run endlessly, okay, to work on a problem. In addition, the algorithm must be general enough so that it can solve like problems, various problems could be in different size as well, right? Generosity here. So that means all of these properties are required, okay? We cannot miss any of them, otherwise it is not an algorithm. Let's see an example of an algorithm here, which is shown as a pseudocode. This is just to find a maximum number in a list, integer list, when we have n elements, okay, n, right? N elements in the list A1, A2 up to AN. And this is not a sorted list, so that the number could be like 100, 9, any number, right? Arbitrary here in the list, for example, and so on. So how to find the maximum value in the list of size n? What happened? Okay, so this is just one algorithm that can do, okay, right? So we can see that starting with a variable max, right? Max is assigned to the first element in the list. So this is A1, this is A2, A3, and so on. So max is here. And then the index I, okay, I from 2 to n, so that the AI, which is A2 here, would be compared with the max, right? So that if max is less than AI, then we update the max with AI, which is A2, okay? So that we keep checking the element in the list AI, okay, A2, and then A3, A4, and so on, to find the maximum value in the list, right? Whenever we find a bigger value, then we update the max to be that number, right? So that means we have to check all the elements in the list, A1, A2, up to AN, okay, to get the result, right? Mm-hmm. Okay, so that whatever the value of n, okay, n could be 10, 20, 100, or even a lot more, then this algorithm can solve the problem, right? Mm-hmm. Okay. Next, let's move on to a searching problem first. Okay, a searching algorithm. That is when we have a list. Okay, a list with n elements, and we want to search for a certain number if it is in the list. Mm-hmm. Okay, so first we have elements A1, A2, A3, and so on up to AN, right? And these are supposed to be, okay, integer or could be real number. And we want to find x in the list, if it is in the list. So that how to do? A simple way is just starting with the first element in the list and check with if it is equal to x. Okay, suppose x is equal to 19. Okay, check if 19 is in the list, right? Check with A1. If not found, then check with A2 and keep doing that until we find 19 in the list, or until we search for all the elements we compare and we could not find 19, right? Then we stop and then report that X is not in the list. Okay, so this is a simple way to do. It is an algorithm as well. An example application of this is just like here, right? In a library, when we check for if like someone has an overdue book or not. Okay, finding if there is an overdue book in the list, something like that. So that the algorithm that we talk about is a linear search. We're gonna see that a little bit in more detail, and then later about binary search, a different algorithm that can solve the same problem. So that the way that we search for a number in the list is shown here using a pseudocode, right? And it is called linear search. That so that we have to understand the pseudocode, how it works, right? So you have this in programming course as well, right? Pseudocode. Okay. Right? So it starts with the first element where A1, so I is 1, and then repeatedly we like check if AI is equal to X or not. Okay. So X is what we want to find out, right? Search for X. So X is a number, integer, right? And keep checking if X is equal to AI or not, right? If it's not, then increment the I, okay, checking with the next element in the list, right? So that would be like A1, then A2, A3, and so on, like that, okay. If X is found in the list, then we know that it is equal to AI. We know the value of I, okay. Then we can report that, okay, the location that we find the X is here, is I, is equal to AI. Okay. Otherwise, okay, if we could not find X in the list, then we report that 0. Okay, location 0 means not found. X is not found. Okay, here. So what we see is that the searching goes, okay, start from the first element and then move on to the next one, okay, repeatedly. Okay. So this is called a linear search. Let's see a different way to search, that is binary search. Right? We talked about this briefly last week as well. Right? The same problem, finding the X in the list. For this technique or algorithm, then the input, okay, the list have to be sorted first, so that right, the A1, A2, and so on are in an increasing order. So that means A1 is equal or this way, right? A3, AN. So AN is the largest element in the list. A1 is the smallest one. Okay, it has to be done this way first before we can use the binary search. Okay. So that what is discussed here would be shown in the, like, can be represented as a pseudocode, okay, pseudocode here for binary search. So let's see this together, okay, like, okay, let me make like a smaller example first, okay, sorted list, let's say A1, A2, A3. So it's just a small list like this. Okay. Suppose, oh, it's gone. Let me write again. 5, 7, 10, something. Okay. A1, A2, 3, 4, 5, 6. Oh, okay. We have, let's make it just A6 for now. Or even, okay, A6, A7. 8 elements. Okay. Let's say n is equal to 8, this one. So with binary search, then we have like here the X and I and J, which are index. Okay, index. So I pointing here, first element in the list, I is 1, and J is here. J is n. And then in the while loop, when I is less than J, right? 1 is less than 7, then M is the middle of I and J. So I plus J is 1 plus 8, which is 9, divided by 2. So 4.5, and then lower bound of this, so it is 4. So M is here. Okay, just like this is now M. M is 4, right? So this is to divide the list into 2 halves, okay? List of size 8. Now we have just list of size 4, okay, two parts of them, right? Where M is pointed at the largest element in the first list. And then suppose, okay, we want to find X, what should X be? Suppose something. Okay, suppose x is any number 38. Okay, you want to find if 38 is in the list. So where are we? Here. Checking if x is greater than am. So that means x is 38 is greater than a4 or not. What is a4? 13, right? So it checks if x, which is 38, belong to the first half of the list or not. That is checking with the largest element in the first list, which is 13. And we see that, no, this is not true. 38 is not here in this list, right? So yes, x is greater than a4. So I is equal to m plus 1. That means now I would be pointed here, would be updated. So that means now this part of the list is removed or discarded, okay? Because x is not possible in the first list, the first part here. And then now we just have 4 elements to work on. And then repeat the while loop when I is less than j. That is, I now is equal to 5, right? 5, j is 8. So m is obtained. That would be the middle between I and j. So now m would be pointed here. Next, right? Because now we have 4 plus 8. So that is 6, right? Hold on. Right. So this is m. Then check if x is greater than am. That is 38 greater than a6 or not. a6 is 38. 38 is not greater than 38, right? So j would be equal to m. That is now j would be pointed here, j. So that means the list now would be updated. We just consider the elements between I and j. So that is okay. This list would be removed. Now we have just only 2 elements left in the list, okay, which are a5 and a6. Then next while loop. Okay, I is still less than j. 5 is less than 6. So what is m now? Next, m would be equal to 5 plus 6. So that is 5. So now m would be updated here, right? So that means the list would be cut into half again. M is here. Next, checking x is greater than am. M is 5. 24, right? Yes, 38 is greater than 24. So I would be equal to m plus 1. So that means now I would be here. Okay. So basically, that this is to check if x belong to which part of the list. Right. So this one is gone. So now what we have is just only one element left in the list, which is 38. Right. Now I and j are pointed at the same element. I and j are the same. So that this while loop, the condition is false. So that would be here, right? Exit the while loop, checking if x is equal to ai. X is 38, ai is a6 equal to 38. Yes. So now we find the x at the location I equal to 6. Otherwise, then it means no, x is not in the list. Okay. So basically, what we see is that with binary search here, starting with the list of n elements, right, size n, and then the list would be partitioned into 2 halves, and then checking like which half that x is possible to be in, okay, because the list is sorted, so that we just check the largest element in each list, okay, in the first list, if it's if x is greater than that or not. If it is, that means x is not possible to be in the first part of the list, right? So that we just remove this one, okay. So the list now, the size is 4, okay, cut in half 4. And then after that, with 4 elements, then we cut half again. So remaining would be just 2 elements in the list. So that is just like 8, then 4, and then 2, and then 1. And check when we have only 1 element, we check if that is the number that we look for. Right? Another example with a longer list is here, this one. Similar way, you can see that initially we have a sorted list, right? So here is A1, and this is AN. What is N? I think N is something, okay, 16 elements, right? Then partition. So we have 8, A1 up to A8, and then this is A16. We want to find 19 in the list. 19 is here, right? But the algorithm doesn't know right now. So it checks the largest element in the first list, which is A8, which is 10. 19 is greater than 10. So that is not possible to be here. So removing this part, and then with the remaining list, cut in half again and check the largest element. If x is greater than this, yes. So we remove this one again. Now we have, first we have 16, right? And then later 8, and then next we have 4. 2 remain here, right? And then 1 left, right? So that we must have just only 1 element in the list before we can check if it is the number we look for. Okay, all right. So that you can see that this could be more efficient than with the linear search. Okay, maybe it's not very clear for now. Okay, but think about number of loops that we have to go through here. With the linear search, the number of loops would be pretty much equal to n or n minus 1, where we have like n elements in the list and we have to check one by one, right? A1, A2, and then A3, and so on, up to AN, if it is equal to x, right? But here, when n is equal to 16, how many times that we go through the loop? 4 or 5 times, right? So that's about like log n is log base 2, okay, is 4, right? So the number of like loops that we go through would be about like log n, but the linear search would be n, okay, n and okay, linear, and this is binary search. Okay, so that we have talked about the definition, right, of algorithms and see a few examples, right, of algorithms for solving problem, finding out like maximum value or searching for something in the list. Then next, let's move on to the second section where we're gonna analyze for complexity of functions, okay, where actually algorithms are like also, right, would be represented as functions as well. Okay, we'll see that next. Growth of function. But this, okay, people also name it as a big O, okay, big O notation or big O estimate. Let me see, anyone is familiar with this, have seen this previously, maybe in high school? Oh, okay, that's all right. And then just in few minutes, then you just know all about this. Okay, so that there are some mathematicians involved, like in just right, initiate this, develop this information, the concept here. Function could be like any function, just like fn is equal to fx, okay, fx equal to x squared plus 3x plus 5, something like function, right? So x could be about the size of the problem or number of elements in the list, okay, like some x, so that we can, given a function, it tells us about how complex the problem is. So that when x increase, the value of the function increase, right? So that, okay, let me see which one. Okay, not right now. X increase, then fx increases. As you may see here as well. Actually, this should be like increasing function. Okay, increasing function. So that when x is here and fx is here. So that means the value of the function increase, or we have a growth of the function. Let's see about the function first, okay, before we go with the algorithm. Function, okay, function f and g. Function of x when x is integer. With the big O notation, here is the main equation that we have to be always follow this one. Okay, that is what we want to do is we want to approximate the value of the function fx. Okay, let's say fx is equal to 2x squared plus 5x plus 19, suppose, something like this. Okay, the function fx may be like complex or having many terms. We want to simplify or approximate the value of this function, okay, using the gx. Okay, and it means fx is the O of gx, big O notation. Okay, we want to find out the gx. What can be gx? Any function that meet to this requirement here. Okay, that is, we must find a constant c. Okay, c. So that when c times gx is greater than or equal to fx, like the absolute value here, and then x must be like starting with something that is k. Whenever x is greater than k, so k is an integer, a constant. Okay, c and k are constants. There could be many possible values of the c and k. Okay, that we can use. They are considered as witnesses. Okay, for this relationship as a big O. Sounds very abstract, isn't it? Okay, so that okay, we'll see more examples. Okay, to understand about this. Let's see about this graph again. Okay, we see the function fx, right? Suppose this is the function here, fx, and then gx is here, okay, times c times gx. So that we have here less than or equal to c times gx. Okay, we see that c times gx could be less than fx for some times here, but when x is greater than k, then this equation is true, right? That means c times gx is greater than or equal to fx there. And then we use gx as the approximation of the function fx. So the constant, we have constant here, c, and also k. K is a constant. When x is at least k or more than that, then this is true. Okay. So that is about big O notation. That let me see. Okay, let's take a look at this example. That should be okay, like that. Verify what it is about the big O notation. Considering a function fx here, which is x squared plus 2x plus 1. And we want to find out if the gx is x squared. That is, if x is less than or equal to c times x squared or not, right? where gx x squared, okay, big O. To show that this is true, okay, then in order to be true, the function fx here got to be considered in this form, right? That is, we got to find a constant times x squared. So how to do this? We got to start with like the largest term in the function of the function, which is this term, right? Largest one, x squared, with the highest degree, so x squared here. And then the next term, 2x, right? So this term would have less value than x squared when x is large. So that we can just like simplify, okay, simplify this term as here, okay. 2x would be less than or equal to 2x squared. And also the last term, 1, is simplified to be less than or equal to x squared. Why do we do it this way? Because we just want to come out with a constant times x squared, right? Constant would be the summation from here, 1, 2, 1, something like this. That's why we simplify each term as x squared, constant times x squared. Just strict, just focus on the largest term in the list first. When x is large, which term would be like the largest term? So it's just the term with the highest degree here, which is x squared, right? So that is how we simplify the function fx as a constant times the largest term in the function. That is x squared. And that is gx. What is c in this case? C is equal to 4, right? And this is true when x starts at what is the minimum value of x that make it true. X greater than 1, right? When x is greater than 1, then this is true. So that means here, this one, x is greater than k. X is greater than 1. So that means this is k. So the witness value k and c here, k is 1 and c is 4. Okay, this is one way to do. Let's see a different way where we're gonna come up with a different c and k. Okay, that is fx is equal to 1, right? And then, okay, equal to, so keep the largest term, and then the rest we can just make it like this one, less than or equal to x squared. To make it true, 2x less than or equal to x squared, x got to be greater than 2, right? When x is greater than 2, then 2x could be less than or equal to x squared. And then this one. So by doing this, then we get here, where now, what is c? C is 3, and this is k. K is 2. But the same result with the gx. This is x squared, right? This one. So with this example, we see that we can obtain different value of c and k. Okay, there could be many possible values that are witnesses of the big O notation that we have. We want to find the approximation, okay, the close approximation of the function fx. Okay, so that's how we got here, right? This one. Okay, let's see further, like considering a function fx and gx here, just two different functions. We just saw that this is true, right? Fx is a big O of gx. And is it true that gx is a big O of fx? Yes. Okay. Why? When the two functions have the same order, or just consider the largest term of the function, they are the same here, which we have x squared. Okay. So that means both functions have the same order, so that we would have fx is ogx and vice versa. Gx is ofx as well. But, okay, let's see the next case when fx is ogx and there is another function, okay, which is hx, which is larger than gx. Okay, so that is considering fx less than or equal to gx less than or equal to, okay, let's say c1, c2 times hx this way. Okay, so that means this is equal to O of gx. Okay, and also fx is also O of x as well, right? Based on the definition of the big O. But just keep in mind that we just want to find a close approximation, right? So that come out with the smallest function possible. Okay, let's see next. Considering an example where fx function is equal to 7x squared, this one, and we got to find out if this is equal to x cubed, this one. Okay, so based on the definition of the big O, it means that this one got to be less than or equal to a constant times this, right? So we must be able to find a constant c here. Okay, so that there are many possible values. Like one of them is when c is 1, okay, we could have this true. When x is greater than 7, so that means k is 7, okay? Or another case, when c is equal to 7, just here, 7x could be equal to 7 times x3. So this is c, and then x greater than 1. So this is k, right? So we have this also okay, right? So we see again that many values of c and k are possible, and the gx can be x cubed here as well. What about the next example? Is the n square is big O n square equal to O of n or not? Show it. According to the big O notation definition, right? Fn or fx. Here, constant times n. Is it possible? Is there any constant c that would make this true always? When n is large, very large number, what could be the c? C got to be even larger, okay, or equal to n, right? But c is a constant. N can be increased. N is a like variable function, can grow. When n is large, n squared is even larger. So that we cannot find out a constant c that would make it this to be true. So that means this is not a big O, right? Okay. And then when we have a function with many terms, as shown here, like we can present the function where the first term has the highest degree here, like this term. So this is actually a polynomial function, right? The first term has a degree n, and then followed by n minus 1, n minus 2 degree, and so on there. We can find out the big O of this function, okay, as an approximation. So it is gx. Okay, let's see how it works here. From this one, an minus 1, and so on are constants, right? They are constants. So that you can see step by step how it works here. See the sign. This is less than or equal to. And then we approach, okay, step by step. So that we can simplify the function, okay, approximate the function. So we have here the x to the power of n and summation of constants, which is a constant, right, here. So that the result is just a constant constant times this. So that is the big O. The big O of this function is x to the power of n. So that simply we can just focus on the largest term with the highest degree in the function, and that is the big O. Okay, big O. Okay, let's see a few more. Okay, then this example. What about a function fn, which is equal to the summation of the first n positive integers? Okay, and we want to find out this now value gn. Fn is less than or equal to c times gn, right? Find out the value of the gn. See that the largest element on the largest value, right? The term would be n, right? So n. So we simplify the smaller term that they are less than or equal to n, so that we would have like something like this. Simplify. So this is equal to n squared. So that means this is the big O, right? The simplification of the function here. And these are the witnesses C and K. What about a next function? Fn is equal to n factorial. Then n factorial. So what is the big O? Big O could be this one, or we can just simply make just n factorial, which is okay. Keep it just like Fn equal to O of n factorial or O of larger function. Okay, so let's take a look at this graph where we see many functions. Okay, starting from like the bottom, a simple one, just like this is fn, right? Simple like a constant, log n, and so on. So that when n is large or n increase, then we see the growth of the function, right here. So this one, n factorial, has the highest growth, or if we have n to the power of n, then that could be something like here. Okay, even more. Okay, right, this one. Okay, then I'll skip like some detail here because it's quite like obvious, and then you can also look at this later on by yourself too. Okay, so we just okay, consider a couple more cases here, okay, which would be helpful for your big O analysis. Okay, the function, okay, fn, fx, gn, gx, these are like can tell us about like number of operations, okay, in an algorithm that used to solve a problem, okay, like fx equal to anything like this, right? Number of operations. When we have like many problems to work on, and we have many algorithms to use, okay, and then suppose that, okay, we already find out that the approximation or the big O of the function f1 is here, g1, and for function f2 is g2. Okay. When we use both algorithms where f1 and f2 are the number of operations required in the problem solving, then we can just combine the two functions, f1 and f2. Okay. The big O of the combination of the functions would be equal to here, max of G1 and G2. So that, okay, we don't have an example here. So let's say like this is, okay. For example, these two functions, what would be the approximation of F1? What is G1? Big O, right? What is G2? Largest term, compare x log x and 2x. So it's x log x. Okay. Then do the summation of the two. Max of x squared and x log x. What is it? That is x squared, right? G1 and 2, G2. By solving finding out the big O of each function, F1 and F2, right? So in detail, that just similar to what we discussed previously. Then we got to make it in the form C times something, right? Something. So this could be simplified to be x plus, could be 5x, okay, square. Consider the largest term, focus on that one. And then approximate the remaining term with the same, okay, like x squared times a constant, something. So this is like a constant c. So it could be 7x here. So c is there. Gx is x squared. Yes. So that, or we can simply look at the largest term of the function. That is the gx, or the big O, right? When we got g1 and g2, then we could find out the overall, compare g1 and g2, and the result would be x squared. Okay. Next one, the product of two functions, f1 and f2. This case, the big O of the function f1 times f2 would be equal to the big O of g1 times g2. Okay. So that the detailed information, the summation of the f1 and f2 is here as well. When we plug in number of the value of the n, then we could see exactly the value of the function, right? The growth of the function. That would be significantly different, okay, for some functions here. That you see that even more in the exercise problems. All right. Then, okay. All right. So let's take a break for now, okay? And then after the break, then I'll let you work on a few problems, exercise problem first, okay? And then we will come back for another section, okay? Complexity of algorithm, this one, small section here. So that could be around 4 p.m. Yes. So we have about almost an hour to work on the exercise problem first. Okay, a few minutes break. And we have today, PTA, Ken and Tanu are sick. They are not here because they are sick. But we have 4 assistants here, your senior friends here from second year. 4 of them, you know them? They are at the back of the room now. Yes. So that they will help us today in the class. Feel free to talk, to chat to them. Okay. So now it's about time to work on the exercise problem. Okay. And then the first page of the problems. First page that contain 4 problems are due within today. Okay, today, midnight, before midnight today. First page, 4 problems หน้าแรกส่งภายในวันนี้นะคะ on LEB2. So that you got to find constant C and K as well for problem number 2. Okay, number 2 and 3. And the rest is okay. But just show your work, how you get to the result. Okay. Attention, please. Okay, let's work on a few problems together here, just to make sure that everyone follows. Okay, and know how to solve all of them, right? Okay. Starting with the first problem, we have to show how we get to the answer, not just say yes or no, right? So let's see. Problem 1, we have A, B, C, D, E, F here, right? So A, find out the function if its big O is x squared, right? So that is to find out if this is true, right? So that means according to the definition of the big O, we must be able to find a constant C times gx, which is this one, right? That one. This is C times gx. For the first problem, f x is 17x plus 11 less than or equal to, right? So look at the term which has the highest value, right? So that's 17x. Okay, we can just take it that way. And then 11, we could even make it like 11x. Okay, this is true when x is larger than 1, right? So we have 28x. We could make even this x squared. When x is greater than 1, this is true, right? And it's c times x there. What is c? 28. C can be any number that make it true here. There could be many possible values, right? So this is O, right? This is for A. Okay, problem A. What about problem C? Okay, C. Fx is x log x, right? Make it in a form with the gx c times x less than or equal to. We see that this term x log x, it's also less than x squared, right? When x is greater than 1, right? C can be 1. Or, okay. Or if we are not sure, we could make even 2. Okay, doesn't matter. This would be for sure, right? When x is greater than 2, this is true. So that's OX like this, x squared. Now we finished 2 functions for problem 1. Okay, so that you could do more for problem others, right? B, D, F, something like that. Okay, so that is, we just have to strict on the definition. This one, right? That is constant times gx. Find a constant c and k. Okay, and you can check that mainly the result would be just based on the largest term of the function, like here. Okay, got to do with x. This is x squared. This is x log x. Okay, right? This one, the big O, this one. And just check if that is less than or equal to constant times this, right? Okay. So that means, okay, some functions would be having the big O equal to x squared, but some others are not, right? They are not all of them having the same big O here. Okay. Let's see about problem number 3. Number 3. We have like a function, like kind of long list here. So this could be considered as the function of like fx times gx. Okay, like here. The upper part is fx and the bottom part is g. Oh, I should not use g then. Let me change it to be f1 and f2. Okay, like this. So that we want to find out the big O. So f1, x1, okay, would be equal to O of g1x, g2x. Just find out the big O of f1 and f2 and then work on this, right? g1 divided by g2. And that means here, g1x is actually focus on this and this, right? Okay. So I leave the detail for you to work on. Okay, the main parts are here, right? Okay. So that this approach can be used for solving the problem down here, problem 4C and 4D. Okay. And then for problem number 4, we have to find out the minimum value of n, okay, so that would give a closest approximation of the function fx. Hello, we are back to the lecture at 4 p.m., right? There is still one more section to cover about the complexity of the algorithm, นะคะ so that you could do the remaining problems in the exercise. So that could take about half an hour for the lecture, I think. Okay, and then you can finish up the first page of the exercise problems, like anytime before midnight today, and do the submission on LEB2. Okay. ค่ะข้างหลังเดี๋ยวมาเรียนกันก่อนนะคะ so let's go back for half an hour lecture and then you could do the exercise problem again after that มีคนแอบกลับบ้านแล้วน่าเช็คชื่ออีกรอบหนึ่ง someone just left I see that ก่อนเรียนก่อนเลยเวลาแล้วอ่ะนะจ๊ะเริ่ม4 โมงนี้เลทแล้ว okay here is the remaining section for today we already talked about function right complexity of functions we know about algorithms so that this is the main application of the big O that is to identify the complexity of the algorithms, how complex it is. Okay, since we know that there are many algorithms out there, right, to solve problems like searching algorithms such as linear search, binary search. Okay, that's what we talk about. So how complex is each algorithm is here. We want to find out like what's the time, what's the amount of time used to solve the problem, or what about the memory consumption used there. So that this is about called the time complexity. And another one is a space complexity. Space means about like memory space in the problem solving. About the time, it is not exactly about how many minutes or hours in solving the problem because that would directly depends on like your machine, your computer, how fast it is, right? So different machines would just take like different amount of time to complete the problem. So that the time complexity is about the number of operations that the algorithm use in solving the problem, just like how many additions, multiplications, comparisons in the algorithm, okay, in solving the problem, like in linear search and binary search that we're gonna discuss next. Okay, and that tells us about the efficiency of the algorithm, how we compare them. We're gonna see about the worst case. In the worst case, what is the worst case time complexity and what is the average time complexity. These are the two different complexity that we have to know. Okay, so let's see about the previous algorithm that we talked about this earlier today, right? That is to find the maximum element in the list. This one, pseudocode. What is its time complexity here? That is finding out the number of comparison. Okay, so the more it is, the more complex the algorithm is. Number of comparison. Where is it in the algorithm here? Shown in the pseudocode comparison. If I is equal to 2 to n, okay, it's here, and also here. Comparing if max is less than AI. So we see that there are two comparison, right? Per loop here, per loop. How many times we repeat the loop starting from I equal to 2, 3, 4, 5 up to n, right? So that would be n minus 2 or n minus 1 loops, right? So that we have n minus 1 loops to go. And each loop has two comparisons. So that's why we have here. The total number of comparison is here, 2 times n minus 1. And then this happens till when I is equal to n, right? I equal to n. And then in the next step, I would be equal to n plus 1, right? Incremented to be n plus 1. And then checking that this condition is not met for I is from 2 to n. When I is equal to n plus 1, then we exit the loop. So that's additional comparison, the last one. So that the total is 2 times n minus 1, number of comparison. So that Fn in this is 2n minus 1. That's the number of comparison for this algorithm. That's how we get the function Fn. And then the time complexity is the Gn. Find out the Gn. What is Gn? Gn is just n, right? When Fn is equal to 2n minus 1, we can approximate it to be 2n, right? Minus 1, right? So this is C times n, constant, right? C is 1, or C is 2 there. N is greater than 1. So Gn, right? Gn is 1. Gn is n. Linear complexity, right? Linear time complexity here. So now we see that, okay, the complexity of algorithm, right, can be obtained when we consider the number of comparisons, right? That's the Fn, function Fn. And then later we find the big O, which is Gn. Okay. Next, let's see linear search algorithm. This one, pseudocode. Considering the number of comparisons again, okay, that's the operation, mainly in this algorithm. Where do we have the comparison? I less than or equal to n, right? I not equal to a, x not equal to ai. So we have two comparison here, right? Loop, while loop. How many times we repeat the loop? When I is equal to 1, 2, 3, 4, 5, up to n, right? So that would be n loops to repeat. And then one more when I is equal to n plus 1. Then the condition is not met, so we exit the loop. 1 here. That's additional comparison to use to exit the loop. And then after that, one more comparison here. If I is less than n, less than equal to n. So this is the last comparison. Okay. So summation, that would be 2, right? Times n, and then plus 1, plus 1, plus 2. That's the function Fn. Number of comparisons in this algorithm, function Fn, equal to 2n plus 2, Gn, right? O of n. How? Fn equal to 2n plus 2 less than or equal to a constant times Gn, right? Okay. So that C can be 4. In this case, n could be greater than 1. So that's K there. So that the time complexity of this linear search is O of n. O of n. Okay. Worst case is that we check all elements in the list, right? So this is a worst case complexity. What about average case? That means we may find the X somewhere in the list, okay, at location I, right? Location I. So that means at the loop I, we find the X in the list. What can be the I? I can be 1, 2, 3, or 4, up to n, right? So that the number of comparison for any I would be equal to 2. So this is worst case, right? For the average AVG, then it would be Fi, right? I would be 2I plus 1, 2I plus 1, number of comparison. So when I is 1, we get 3, right? 1, 2, 3, up to n. Find the average of the function here, right? There are n cases. So this is Fn. The average is still O of n. So this is a linear search. What about binary search? Binary search, starting with n elements in the list. Okay. Then how many times we get into the loop here? Just like if we have starting from the size n divided by 2, 4, 8, right? Divided into half, half, half again and again, right? Until just only one element left in the list, right? Okay, so that the number of times we get into the loop here would be equal to k, okay, k loops. What is that k? K is equal to log n, okay? That is, first we have this is equal to 2 to the power of k first, and then after that it's and so on till we get k equal to 0 or 1. Okay, just like if we have 16 first and then 8, 4, 2, 1, right? So that the number of times we get into the loop would be equal to k loops for 2 to the power of k integer. Let's solve this. So this is n, right? So k is log n. This is log base 2. So that in this course, okay, the default is the log base 2. Okay, log n is the log base 2 there. So that how many comparisons do we have? One here first when I is less than j, and then one more here when x greater than or equal to greater than am or not. Okay. So that means in each loop, while loop, there are 2 comparisons. So the total would be 2 times k, right? 2 per loop. We have k loops. And then to exit the loop, that is when I is not less than j. That's one comparison. And then the last comparison, check if x is found or not. One more. So total would be 2k plus 1, plus 2. So that means the here fn is equal to 2k plus 2, or it's 2 times log n, right? Plus 2. That's a function of n, fn. So the gn would be O of log n. Since, right, this is a constant here. So that means we approximate the function fn. We find the big O, that is log n, which is, we know that log n is less than n, right? So that means this algorithm is less complex than the linear search. Okay, that's a binary search, right? Less number of comparisons, okay, more efficient, faster to solve the problem, okay? And then there are a couple more, maybe just one here shown, like for a matrix multiplication. Everyone knows how to multiply matrix, right? Even binary matrix or any matrix, you know how to do that. We can come up with algorithm or pseudocode, okay, to do the operation, right? So that there would be some while loop inside. Basically, there are operations which are addition, right? Addition and multiplication inside, just that, like. Okay, just like when we have 2, then this one and this one, just like to find A times B equal to C, then the Cij, right, would be something like this one plus this one, and inside there is a multiplication in the term, right? And then there is addition, like of multiple terms here. to find each entry in the matrix C here, right? We have C. So it's a Cij there. Okay. So that number of multiplication and addition can be can be obtained there. And that would be n multiplication and n minus 1 addition here. And since we have n square elements here, so that the result would be n squared times 2, right? n 2n minus 1. So that is a function fn, telling us the number of operations in this matrix multiplication. You can see the pseudocode of matrix multiplication, okay, in the text as well in the book, and you see similar problems in the exercise problem. So that just like here, okay, it is here. Oh, okay, I did not see that at first. Okay, this one. So we see that there is a for loop here and here for I, for J, right? And for Q as well here. So that is about M, N, and then some number. And this would be N plus N, some number here, right? So we multiply them all. This is M is less than N. So the approximation would be N, and then C times N, approximation. And then we multiply them all. Just like this is F1, F2, and then this is F3. So F1 times F2, F3 would be O of G1 times G2 times G3, like that. So that would be O of N, right? Okay, so that we can apply this one, right? The way we discussed when we have multiple functions and then we know the complexity of each function, then we can just combine them, right? Depending on if we have the like multiplication or addition here of the function. We use this, right, as the product because we have to do all the tasks, right? Okay. So that's pretty much all that we have here. Complexity of algorithms, right? Once we are able to analyze the algorithm, finding out like number of operations that tell us about the time or complexity of the algorithm, okay, number of comparison, addition, multiplication, something like that. And once we know like exact amount of time to do each operation, then we could find the exact amount of computation time as shown here. So this is a function fn, right? So if we have very complex function, okay, when n is here very large, then it could take hundreds of years to solve the problem, not in anyone's lifetime. Okay, that's why, right? We aim for efficient algorithms. Okay, make it be able to finish within reasonable time or minimum, if possible. Okay, the complexity of the problems that we use algorithms to solve. Okay, there are some terminology here that you see or you may have seen this. Tractable. Tractable means like solvable. We can handle that, okay? Can be solved. If not, it means intractable. But it has to do with the polynomial time used in problem solving as well. What is the polynomial time? Polynomial complexity, this one. You may see later we talk about big O, right? Big O of the function, big O. Actually, there are some other variation like big theta, okay, and in big omega. They are similar, just like one is considered like lower bound, upper bound, something like that. But here the same thing is that polynomial complexity is this one, O of n, b is a constant. If the complexity is larger than this, then the problem becomes intractable, okay, which is different from unsolvable. Okay, this is not good, right? That means no existing algorithm can solve the problem. Another one that you will see more and more later on called the NP class. NP stands for the non-polynomial time complexity. That means it requires even longer time. That means OGN is greater than O of n to the power of b. It requires like right, high time complexity in the problem solving, which contains like challenging problem here, so that people are trying to develop efficient algorithms to handle the NP class problem. And that's it. Okay, that's all for what we have today. So today we talk about the algorithms, right? What they are, some example of them, growth of function Fn, right? Which is O of big O notation, O of Gn. And then we find out, analyze for the complexity to as a function Fn, and then we could do this next. So that later you may like invent or develop your own algorithm and be able to find its complexity as well, okay? But that's not it could take a while to do that. But now for the exercise problem, okay, this one, right? Okay. Problem number 1 to 4, okay, on the first page is due today, okay, before midnight, okay? And the remaining part would be just by Tuesday before the class, okay? So that the last few problems would be just about what we just discussed, right? Complexity in the problem solving, the algorithm, right? We see some pseudocode here, for loop, while loop, something. Find out first number of addition, okay, Fn, and then find out the Gn. Okay, that's problem number 6. And then this is already Fn, right? Fn. And then each operation takes the 10 to the power of minus 11 seconds. Then how much time can we complete, or can we complete within a day? Right? So 24 hours. How many seconds do we have within a day? Find what is the largest n. Find out the n. Okay. So the rest should be okay. And the last problem, we have addition and multiplication. Where are they? Addition, right? Add, multiply is here. Okay. All right. That's all. Okay. Then you can resume your exercise problem, working on the problem, and let us know if you have any question. So that we could spend time here till 5. Okay, and then you can go home. That's fine. Okay, and we'll finish the rest later on before midnight. Or it's okay if you like to leave now. Okay. All right. Thank you for your attention. And then I'll see you next week. I see that many of you are so sleepy.